Okay, in this video, we're going to talk about thermochemistry and as it relates to stoichiometry, and we'll also talk about writing thermochemical equations. But before I get into that, I just want to make sure that I give you the conversion correctly because I have this gut feeling that I gave it to you wrong in the previous video. And I just want to double check, just make sure you put this in your notes. 1 kilocalorie, which is capital C calorie, is equal to 4.184 kilojoules. 1 lowercase calorie is equal to 4.184 joules, not kilojoules. Okay, so 1 kilocalorie is 4.184 kilojoules. 1 small lowercase calorie is equal to 4.184 joules. All right, just in case I messed up in the last video. Okay, you guys remember stoichiometry from chapter 3 and chapter 4 and chapter 5, and here we are with stoichiometry again in chapter 6. But in this stoichiometry here, we are dealing with a delta H value. So when you're writing a thermochemical equation, that means an equation of a reaction where you are paying attention to either the heat evolved or the heat absorbed, you're going to always have a delta H value or a Q value as part of that equation, okay? Just like with all the stoichiometries in previous chapters, we have to start with a balanced chemical equation. So the one I have up here is methane, CH4, plus oxygen. This is just burning of a hydrocarbon, so it's hydrocarbon combustion. Will always give you carbon dioxide and water. Now, reading this equation, this says 1 mole of methane gas is going to react with 2 moles of oxygen gas to produce 1 mole of carbon dioxide gas and 2 moles of liquid water. And the delta H value, this should be up here, but I didn't have enough room. The delta H value is negative 890.3 kilojoules. So basically, they're saying that this is an exothermic reaction, and 890.3 kilojoules of heat is evolved when this occurs. Now, a thermochemical equation always has a delta H value or a Q value there. And the negative sign will tell you that it's exothermic. The positive sign will tell you that it's endothermic, okay? A thermochemical equation also always has these coefficients as molar quantities, not molecular. So you can actually use fractions in a thermochemical equation. You can divide everything by 2. Like this could be 1/2, and this could be 1, and this could be 1/2, and this could be 1, and then you would divide this by 2 also. So you're allowed to have fractions in a thermochemical equation because there is such a thing called half a mole. But in regular equations where the 1 could stand for a molecule, you can't have half a molecule. So one more time, thermochemical equations, you are allowed to have fractions as coefficients, and you're going to be seeing that. The other thing about thermochemical equations is that you have to write the phase. You have to tell me if it's a gas, a solid, or a liquid. Okay, so I don't know if OWL forces you to do that, but when you're doing your labs and on written portions of exams, and you're writing a thermochemical equation, you must write down the phase. Okay, let me just put some parentheses around this L. All right. Okay, so this is our balanced equation, and what is the question? It says, how much heat could be obtained by the combustion of 10 grams of methane? All right, so we're going to start off by writing 10 grams, 10.0 grams of methane. Now, just like regular stoichiometry, we compare everything using the coefficients of the balanced equation. But in the thermochemistry stoichiometry, they want you to compare one of these things to this, to the delta H. So basically, for every 1 mole of methane, you're going to be producing 890.3 kilojoules. Okay? So we're going to write down they give us grams, so obviously we're going to have to change grams to moles, just like we do with all the other stoichiometries. So we're going to get the molar mass of methane. So 1 mole of methane, carbon's 12, hydrogen's 1, so approximately 16.0 grams of methane. Okay. Now we can use this 1 and relate it to this. All right, I'm going to say for every 1 mole of methane, I'm going to be evolving 890.3 kilojoules. And a lot of students will say, well, do I put the negative or not? Let's deal with the negative at the end. All right, so right now, let's just do the math. 10 divided by 16 times 890.3. Get your calculator, and you're going to get 556 kilojoules. So, 2 ways of answering this question. You can say 556 kilojoules of heat energy is evolved. Or you can say Q would be equal to negative 556 kilojoules. Or delta H is equal to negative 556 kilojoules. So the only time we use the negative is if we're relating it to the Q value or the delta H. If you're just saying how much heat is evolved, okay, we're getting 556 kilojoules of heat evolved. Okay, so that's an example of a stoichiometry problem. They're really, really easy. Just make sure you have a balanced chemical equation, and then just, you're creating a molar ratio with whatever substance they give you information about and relate it to the delta H value. Okay, now the other topic that I want to do in this video that is on the what you need to know list is writing and manipulating thermochemical equations. So here's a thermochemical equation. This is the equation for the Haber process, the process that creates ammonia. All right, so we're going to have 1 mole of nitrogen gas is going to react with 3 moles of hydrogen gas to produce 2 moles of ammonia gas. And delta H for this reaction is equal to minus 91.8 kilojoules. So you can see that it is an exothermic reaction. 1 mole of nitrogen reacts with 3 moles of hydrogen to produce 2 moles of ammonia, and you're going to be producing 91.8 kilojoules of heat. Okay, that's how you write a thermochemical equation. Molar quantities, delta H, and your phases. How do you manipulate it? Well, what if I want to produce only 1 mole of ammonia? What do I do? How do I manipulate this so that I produce just 1 mole of ammonia? Well, in order to produce 1 mole of ammonia, I need to divide everything by 2. So I'm going to take this 1 and divide it by 2. So that becomes half a mole of nitrogen plus 3/2 of a mole of hydrogen. 2 divided by 2 is 1. 1 mole of ammonia. And whatever you do to the equation, whatever you do to all these things in the equation, you have to do the same thing to the delta H. So since I divided everything by 2, I have to divide this by 2 also. So delta H of this would be 2 into 9 is 4, 2 into that's 5, 45.9. I think that's what I have here. Yes, negative, again, it's going to be negative 45.9 kilojoules. Okay, so that's manipulating a thermochemical equation. Whatever you do over here, you have to do to the delta H. Okay, what if you want to flip the reaction? Meaning you want the decomposition of ammonia, not the synthesis of ammonia. You don't want a combination reaction, you want a decomposition reaction. So I'm going to go back to this one. And I want this to be turned into a decomposition. So I'm going to flip the whole thing. So I'm going to put the 2NH3 over here. And then my products are going to be these guys, nitrogen gas plus 3 hydrogen gas. Now, guess what you do to the delta H? You flip the equation, you flip the sign of the delta H. So now when we flip the equation, the delta H becomes positive 91.8 kilojoules. So you turned it from being exothermic to now being an endothermic reaction. Okay? So that's a quick summary on how to manipulate thermochemical equation. Let me do another one for you guys. Yeah, here's one. Okay. This is, again, learning how to manipulate thermochemical equations will help you later on when we start playing around with Hess's law. All right, I've got 8SO2 will give you S8. Plus remember, sulfur is one of those polyatomic molecules. You remember how there are diatomic molecules, hydrogen, nitrogen, chlorine, and all the halogens. And then there's phosphorus, likes to exist as P4, and sulfur, it likes to exist as S8. So if you decompose 8 moles of sulfur dioxide, you will produce 1 mole of S8. And we got to put the phases here. Okay. This is a solid. And then you will also get 8O2 gas. All right. This over here is, where's the delta H value for this? Delta H is equal to 2.39 positive 2.39 times 10 to the third kilojoules. So it's an endothermic reaction. So when 8 moles of sulfur dioxide gas decompose to produce 1 mole of S8 solid and 8 moles of oxygen gas, you need this much energy absorbed in order for this to happen. Okay, so what if the question is, write the thermochemical equation for the dissociation of 1 mole of sulfur dioxide into its elements. So if I just want the dissociation of 1 mole of sulfur dioxide, what does that mean? It means that I have to divide this by 8, so I have to divide the 1 by 8 and divide this by 8 and divide this by 8. That's your manipulation. So this would become 1 over 8 S8 solid plus 1 O2 gas. And then you take this value here, 2.39 times 10 to the third, and divide it by 8. And I think I have it calculated somewhere, 296 kilojoules. I hope that is right. So delta H is positive 296 kilojoules. Okay? What if I wanted to flip it? What if I wanted the synthesis of this? What would I do? I flip this, and then what happens? This is changed. So anytime you flip an equation, turn it from a combination to a decomposition, or a decomposition to a combination, or whichever. If you're flipping, if you think of it as the reverse reaction, you have to change the sign of the delta H. Okay? Anytime you're dividing if you're dividing by a certain number, you have to do the same thing to the delta H. Okay, I think that covers manipulation of thermochemical equation, and that way we can go ahead and get started on the concept of calorimetry and heat capacity, and specific heat. Your lab deals with calorimetry and a coffee cup calorimeter, so we'll talk about all of that in the next video.